In engineering, we frequently encounter situations where we're going to want to compare between populations, or maybe two different processes, or perhaps two different treatments, maybe even the difference between products, say tire brand A and tire brand X, and whether there's any statistically significant differences between them, or it might even just be in a business context between two strategies approaching the same kind of situation, and which one is more effective than the other. Here we're taking a look at a very common situation that's out there, and that is that we know that we have an aging and somewhat geriatric civil infrastructure. Civil infrastructure is more than just roadways, it's also pipe networks, and in this case we're taking a look at one of the rehabilitation techniques for municipal pipeline networks, where you can insert flexible liners inside existing pipes, and you'll accomplish a couple of things there, not only providing a new waterproof lining, but you also potentially have a so-called maintenance-free kind of system, and you'll change the coefficient of friction on the inside of these pipes. You'll make them function a little bit differently, typically sort of improved. And the question that we're really after here is, does a particular fusion process increase the tensile strength of the liner? So we have data from two different processes here, one where we have no fusion, sample size of 10, and one where we do have this fusion process where the sample size is 8, with the corresponding summary statistics that you see here. Now, unfortunately, both cases we have relatively small sample sizes, and they're not the same size either, nor do we have any particular reason to believe that the standard deviations of the two should be the same, and clearly we have some sort of a difference in the mean. And so that's one of the questions: is this a statistically significant difference, or is it not? So how do we handle this when we're going about this now with two different populations that we're working with? Right? And so our approach here is to first be very careful in our notation. So this 1 and 2 is with reference to just presenting the data. Now, as we start to work with this, let's do a little definitional work here right up front. Let's let mu1 be our designation for the true mean of population 1. That's the no fusion process. And of course mu2 will be the true mean associated with population 2, and that's the fusion process. That notation is important just to clarify it. Of course, it doesn't matter if we do 1 or 2, but we want to, of course, be consistent enough with what we have up at the top, with how we define the data. And so now as we go and start thinking about our null hypothesis, for which we're going to end up testing, it might seem obvious that what we want to do is demonstrate that this new process actually does have an influence, and an influence in the direction that we would desire, that is increased tensile strength. But what we're going to actually do then is have the null hypothesis set to that the two population means are the same. Because what we're going to hope that is going to happen is that our test data is going to provide credible evidence that says that the null hypothesis ought to be rejected. Right? Another way to express this, rather than mu1 equals mu2, is that, well, the difference between the two means is 0. And it's going to be this form that's going to be easier to work with when we get into the actual calculations and pulling out values from tables, that sort of thing. Right, so our alternative hypothesis, HA or H1, is not going to be mu1 does not equal mu2, but rather it's going to be mu1 is less than mu2, because that's our area of interest. Or again, that mu1 minus mu2 is less than 0. Now we could have just as equivalently posed this in the other way: mu2 minus mu1 was greater than 0 if we had wanted to. We're just simply going to, out of preference here, just use it in this particular way. Okay, and so we come down to the real question in words: is there convincing evidence that the true average strength, that is the tensile strength, for the no fusion process is less than that where we did use the fusion process? Those words are important to connect with the math because there's not a quite as direct interpretation there or linkage there. You have to really sometimes think about it in a lot of these problem statements that you're going to see in your homework and that type of thing. And that's a little bit of an art form just itself to be able to translate this kind of a statement, which usually isn't even quite this explicit. Sometimes it takes a lot of work just to figure out what really needs to be tested. What is it that we're really after? Maybe not quite as much in our homework style kinds of problems, but in practice that's not necessarily such a easy thing to create. So the test statistic that we're going to go after here is, well, note that since we have a small sample size, right off the bat you ought to be thinking that small samples, potentially the t-test is going to be valuable, and then go the next step further and say, well, we don't know the variances, that hasn't been given to us for the populations, so since we don't know the variances and we have small sample size, that right away is going to put us right into the t-test. And so we'll define our test statistic to be the difference in the two means. Right? In whatever order you choose, way back in your definitions up here, you want to keep the same order here, minus then the mean of that difference, so mu1 minus mu2 in general, and then we're going to have our standard deviation down at the bottom. Now we have a mixed situation, so we're going to do a square root of sum of the squares type of approach for our sample variance, and really sample standard deviation associated with the sample mean. That's really what we're playing with here, is not x1 minus x2, but rather the sample mean of population 1 minus the sample mean of population 2. Right? And another way to think about where that denominator comes from is go back and think about if I had two random variables, x minus y, a linear function here of two random variables. Well, the mean of that would equal the mean of x minus the mean of y. The variance of that difference of x minus y would be equal to the variance of x plus the variance of y minus then, or I'm sorry, plus 2 times the correlation coefficient times sigma x times sigma y. If these two are independent, and we're certainly going to assume that with two different populations, then the covariance will be 0. So no covariance term, mixed term sitting out here. Okay. Now, if these aren't just with the random variables, but rather they're associated with the sample sizes or the sample measures, well then we're going to get a division by n1 and n2. Right? And hence, really all we've done is come in and substituted for those two. And that should give you a little bit of a hint that if we did actually know the population variances associated with our underlying processes, then we could come along and directly go into here, and if we had that kind of situation, then that wouldn't be t anymore, it'd be z. We'd be using the normal distribution instead of the t distribution. Right? So for our specific situation then, our computed test statistic, then we've got 2902.8 minus 3108.1, and note that in our null hypothesis situation, mu1 minus mu2 is 0, right? And we oftentimes, and it's frequently easier to call this thing delta, and we're going to have that equal to 0 in this specific case, if that's what we're testing on in our null hypothesis. And then divide by the square root of the sum of the square, so 277.3 squared divided by 10 plus 205.9 squared divided by 8. Now note, the 10 and the 8, the sample sizes are not squared. Easy to make a mistake if you're processing this by hand. And of course you're going to grind this all out, but because we'll be using some of these results later, the numerator is 205.3 but a negative, and the denominator is 113.97, and that equals about minus 1.8. So that's our T0 value that we'll use to enter our tables, T-tables. However, we need to know what the appropriate degrees of freedom are to use. And now we've got two different samples, and so the question becomes, well, how do I mix those together to come up with a single number? Right? And we'll talk about some of the other formulas that are in your textbook, but we're going to go straight at the one that's associated with two different populations with the variances not known and not equal to each other. And we're going to get something similar to what we had before with sort of a sum of the squares kind of approach, but it's going to be the first variance, S1 squared over N1 plus S2 squared over N2, and that whole quantity is squared. And then down in the denominator we'll have S1 squared over N1. That will be individually squared and divided by N1 minus 1 plus then similar expression for the second population. Right, that looks like a kind of a complicated expression, and indeed it does get kind of nasty. And so one of the things to do, especially if you're processing this by hand, is to do some of the calculations as partial calculations and then substitute in. And even then, in this case, these numbers get pretty large, because note, that thing and that thing are both going to get squared again. And so I'm not going to show you all the little bits and pieces here, but we get 15.94. Now the question is, well, what do you do with that? And we want to play it on the conservative side, so what we do is we truncate that. The smaller the degrees of freedom, the wider the t-distribution is going to be that's associated here with this guy. So we'll use 15 for our degrees of freedom. Right, now, when we go look this up in our t-tables, remember that what the t-tables are going to provide for us, at least the ones that you have specifically in the Montgomery and Runger text, and they're all potentially a little bit different, are they're going to give us a t-value out here in this right-hand tail, in the area that's associated with that t-value. Right? For us, we have a t15 value that's equal to a minus 1.8, but what we have in the table in the book is for the positive value. So, of course, all we really have to remember is that this is symmetric. And so we just want the one-sided one, and effectively here we're getting the p-value. When we go look this up for 1.8, our p-value is going to be 0.046 associated with either the positive 1.8 or the negative 1.8. We actually are wanting the negative one, the lower side, because we wanted a one-sided hypothesis test. Right? Now that p-value of 0.046 then can be compared to our alpha value, which we haven't stated, and for really two different reasons. One of which was to illustrate, and this is really the primary situation, that for alpha equal to 5%, significance level of 5%, we would reject our null hypothesis in favor of H1. Which of course was that, gee, there was a statistically significant difference between mu1 and mu2. Right, so here's the second reason why I didn't state ahead of time, and that is that for alpha equal to 1%, we would not reject our null hypothesis. Maybe it should, maybe it shouldn't. Right? We're real close to that. If this is enough convincing evidence and we're ready to go for that, then we're good. But gee, that's 0.046 is pretty close to that, and it's even better if we can get to alpha 1%. Although remember, if we take a smaller alpha, we increase the probability of beta, our type 2 here, and we're going to get into that here later on. Before we do that, I want to address two other aspects of that, and that is, if we had defined our null hypothesis slightly differently, look what happens. Let's define the null hypothesis is that the difference is equal to minus 100. Right? And that's about half of the actual difference we saw between those two particular samples. Right? And if we do that, the way that changes our processing is that delta is not 0 anymore. Now it's minus 100, because remember, delta was our difference between mu1 minus, or our difference between mu1 and mu2, or mu1 minus mu2. Right? And that changes then the calculation of our test statistic. It becomes now, instead of negative 1.8, it becomes minus 0.92. Right? We still have the same degrees of freedom of 15, but our p-value is going to change. And it now becomes about 0.188. It gets bigger. Right? And that's, of course, much larger than our alpha of 5%. And so even under that rule, right, we would not have convincing evidence to reject our null hypothesis. And that's an important understanding, that up here under p-value of 0.046, yeah, it meets the standard for 5%, right? And we would reject H0 in favor of H1, except for, note that it doesn't take that much. I mean, if this is true, we want this to be true in some sort of significant way, right? And from a probability standpoint, well, that statistical significance is associated with the 5%. But from a practical kind of significance, note that if there's going to be any significant difference here between these two, right, well, this would seem 100 psi out of the approximately 3,000 that we're talking about isn't a large amount. And under that kind of a difference, then we really don't get much in the way of statistical significance, right? In fact, we fail the statistically significant test. So that's not good. that suggests that maybe something else is that might want to approach this from a slightly different kind of perspective. Right? Now, before we head off and talk about confidence intervals for the differences in the means, and then get into the type 2 or beta error, I want to just point out that we did this for small sample sizes. We did it for unknown variances that were assumed not to be equal to each other, and that's really part of the point that you'll see in your text in grand detail, that there are some simplifications, and really quite a lot, if there are a variety of things that happen. One, if our variances are the same and they're known, we can use a pooled estimator approach that you'll see in your text. Really what that means is that we're going to simplify that big, long, complicated expression associated with the degrees of freedom and the variance. Right? That'll get a lot simpler if those two are known and if they're the same. Now, they could be known but not be the same, and that would still simplify some of our expressions a little bit. For instance, we would be able to use the normal distribution instead of the t-distribution. Right? If normality is known, or n1 and n2 are large, right, then we can use the standard z01 instead of having to use the t-value. Right? And that allows us to do a lot of interesting things in terms of calculating type 2 errors and calculating what the sample size ought to be in advance for a given error range that we're interested in. There's a lot of things that can go on, and sometimes you'll make these assumptions before you run the experiments, just to run the sort of case study or the what-if scenario, and then you'll go and conduct the test and then ask the question, well, did we end up with things that were along with these assumptions? And even if you violate some of those assumptions, that can be okay, because sometimes you're using this just to get a handle on what the design of the test ought to be.